We're into chapter 16, I think, and thermodynamics, and we were talking about really the rest of thermodynamics. So we talked about entropy, which is delta S, and we talked really about the idea of delta S, which is it is related to sort of disorder. And when disorder increases, so does really the entropy. And that will make the change in entropy a more positive value. Opposite is true if sort of the disorder there goes down or the order increases. We have a decrease in the entropy, and that is represented really by a negative value that we see. We talked about we could calculate what is referred to as delta S of the universe, and that is our delta S of our reaction, our system, plus the delta S of our surroundings. And there's a couple of different ways that we do calculate each of those things. Really, the delta S of our surroundings, delta S of our reaction, our system, is really the delta S of all of our products minus the delta S of all of our reactants. So these are typically values that we look up in the table. We do use the coefficient like we talked about when we did delta H, and we do products minus reactants. Remember that this alone will not tell you if the reaction is spontaneous or not, but it will tell you that either order is increasing or decreasing as a result of that. Remember, you could also make a good prediction based on sort of gas molecules. If you make more gas molecules than you started with, you'll have a lot more disorder happening, and the change in entropy should be positive. And vice versa, if you sort of make less gas molecules than you started with, you would create a more state of order, and you would have more of a negative value for your delta S of the reaction. The delta S of the surroundings is related to really the type of reaction that's happening, and really the delta H of the reaction over the temperature in Kelvin. And it's really sort of an opposite relationship as we talked about. If the reaction is exothermic, your delta H value will be negative. And that negative and the negative in this formula will turn your delta S for your surroundings into a positive value, which is what you would expect under normal sort of temperature conditions, as the surroundings would be picking up all the energy from the reaction and thus have a lot more energy, a lot more disorder sort of happening. People would be moving quicker if there are gas molecules, and you expect a little bit more increase in the disorder. Opposite would be true if the reaction was sort of endothermic. If it was endothermic under normal conditions, that means the surroundings is going to supply the energy to the system. The result of that is the surroundings then will lose some energy, and everybody in the surroundings will kind of slow down, if you want to think about it that way. They won't be moving as fast, and it will create a lot more order than there was before it sort of gave away its energy. And that would result in a negative delta S, as our delta H there would be obviously a positive number with the negative in the formula. We'll turn our delta S of our surroundings into a negative number in that situation. Remember a couple of things in terms of units. Temperature does need to be in Kelvin, right? Delta H is typically in kilojoules, but S's are typically in joules. So if you are going to sort of add these together like we did in an example and to calculate the delta S of the universe, you may want to make sure everybody's sort of in the same units. Otherwise, obviously, if you add kilojoules and joules, you're going to get the wrong answer, as they are off by a factor of 1,000. The reason we need to do this is we can add them together and calculate the delta S of the universe. And if we do calculate the delta S of the universe and end up with really a positive number, that would mean that that reaction is spontaneous the way it's written. Obviously, the opposite would be true. If you ended up with a negative number, it would mean that reaction is going to be non-spontaneous the way that it is written. Now, we also talked about Gibbs free energy, which, much like the name implies, is free energy available to do some type of work. And there's a couple of different ways that you could calculate Gibbs free energy, and we'll see maybe another one as well today. But we can, just like any sort of thermodynamic value, sort of equation or value, we could just use the equation in the thermodynamic table and do products minus reactants. So we definitely can calculate our delta G of the reaction by the same idea as what we do with H or even S, delta G of our products minus the delta G of our reactants. this clearly would be a situation, as we talked about, that if that's pretty much all you're given is the reaction or equation and really nothing else, that's probably what you should do. If you want to calculate delta G, go to the table, find everybody, do your products minus reactants. Now, if you happen to have some other values given to you, like maybe a delta H, maybe a delta S value given to you, or maybe you calculated previous to that, you could use this equation, delta G is equal to delta H minus T delta S, which I think we were looking at the very end last time. And this is our free energy, that's our enthalpy, that is our entropy, and that is our temperature, again in Kelvin. This is definitely the equation that if you use, you want to be really careful with units. Again, typically our S is going to be in joules and our H is going to be in kilojoules. You got to do some type of conversion. Again, otherwise you will get the wrong answer here. Most of the time, delta G is given in kilojoules. So, it's really up to you. I personally, will usually go to joules and then at the end divide it by 1,000 and convert it back to kilojoules at the end. But you definitely could go everybody to kilojoules and sort of put it in. But you definitely got to do that conversion. Otherwise, you will run into some trouble. Clearly, this version of delta G would be a good one to use if you have the H or S value given to you with the temperature. Why reinvent the wheel and go calculate everything separately here? That would be probably the right one to use in that situation. We also talked about that you can sort of analyze this value or this equation, which I think is what we did at the very end there. And depending on whether or not you have sort of a positive H or a positive S value or negative S and negative H value, you can make a pretty good prediction as to when maybe this reaction would be spontaneous, under what temperatures, and when it might not be spontaneous. So for example, just if we had a delta H that was positive and a delta S that was negative, what that would do in this situation is that negative there would turn that into a positive on the back end. We would have a positive delta H, which means no matter what you do here, your delta G is always going to be positive at any temperature, and that would mean it would be non-spontaneous. So unlike delta S, we can use delta G's value to determine whether or not a reaction will be spontaneous. And if delta G is negative, it's going to be a spontaneous reaction. If delta G is positive, it will be a non-spontaneous reaction. And delta G would equal 0 in a equilibrium type of condition. Remember, an equilibrium type condition, right? We got forward and backwards happening at the same time, right? The rate of those forward and reverse reactions, which means ultimately there's really no change sort of happening, right? So everything's sort of balanced at that point, which is why, again, those things typically will equal 0. Same thing as well if you had a positive delta H and a positive delta S, that would mean that the only way for really this backside to beat out the front side there of the delta H is you would need a really high temperature to do that, to make the joules. Because remember, again, that the S is at joules and the H there is at kilojoules. So you're in a factor of 1,000 off to begin with. So you would need a really large temperature there for that reaction to basically become negative in terms of the delta G, large temperature to do that. Obviously, at lower temperatures, it would be non-spontaneous in that situation. Yeah. Delta G is Gibbs free energy. So it's basically energy available really to do some type of work. And that's what it stands for. Yeah. Other questions? And we can use delta G value sort of directly there to figure out whether or not a reaction would be spontaneous the way that is written. Other questions? All right, so I think that's where we sort of laid up there. So let us continue on here. So if we have this reaction here, a little calcium carbonate, going to make some calcium oxide and some carbon dioxide here. And the delta H value for this reaction is 177.8 kilojoules. And the delta S is 160.5 joules. At 25 degrees Celsius, is this reaction spontaneous? So take a moment and determine that. Here to roll with this equation, minus T delta S. In this case, we're just going to plug it in. We do want to obviously convert that into Kelvin. So we'll add a 273 to it, gives us a 298 Kelvin. So putting that in here, we got our delta H, which is 177.8. I am again going to multiply it by 1,000 to convert it to joules. So everybody's in the same unit. Again, if you left it in kilojoules, you should have converted hopefully the delta S to kilojoules. So everything would be in the right unit. Minus my temperature, which is 298, and my S, which is in joules at 160.5 Kelvin. And if we do all that good stuff there, we're going to go 177.8 times 1,000 minus 298 times 160.5. Going to give us, go down here, 1,29971 joules. At this point, I'm going to divide by 1,000 to convert it back to kilojoules. So maybe like 130 kilojoules or something in that ballpark there. Any questions on that there? Is this reaction spontaneous at 25 degrees Celsius? The answer is no, as our delta G value here is positive. Delta G meaning non-spontaneous at 25 degrees Celsius. Any questions on that? Now, could we, if we wanted to figure out, well, it is not spontaneous at say 25 degrees Celsius, is there a temperature at which it would become spontaneous? And we could also use the same equation to help us do that. So if we wanted to sort of figure out at what temperature this reaction would become spontaneous, we could use this equation. Essentially, to become spontaneous, we need a negative number, which means in this case, we're going to set delta G equal to 0 in this case. And that would be any number past that would be obviously a negative number. We're going to rearrange this equation and solve for temperature. We're going to divide that over, which means our temperature here would be our delta H divided by our delta S in this particular case. So putting in our numbers here, I'll go up a little bit. I am once again going to be cautious of my units. They have kilojoules on top, joules on the bottom. So again, I'm going to convert my delta H into joules by timesing by 1,000. So I am in the right units on both top and bottom. Again, you got to do some type of conversion. Your call, really, whichever one you want to do there. So if I do that, I end up with 177.8 times 1,000 divided by 160.5. Going to give us 1,108 Kelvin, which if we convert that 1,108 Kelvin into Celsius by subtracting 273 from it, that's going to give us a temperature of 835 degrees Celsius as to what you would need to do to get this reaction to become spontaneous. That would technically be the minimum temperature at which this reaction would become spontaneous. First off, any question on that calculation there? By the way, this is sort of what we would expect in this situation. As we just talked about, our delta H value here is positive. Our delta S value is also positive, which means we need a really large temperature here to overcome the first part of it to make the delta G negative. And I would say 835 degrees Celsius would qualify as a really high temperature. In order to do that, 25 degrees is not going to cut it to make it spontaneous. It's just not a high enough temperature to do so. That is also, thank goodness, what we see on the graph here, that number right there at 835 degrees Celsius. That is a graph of temperature versus pressure of CO2. And in this reaction, the only gas there is CO2, which is on the product side. So the only way to get pressure would be you need to make that CO2 gas, which means that reaction has to happen. And as we can see from the graph, frankly, it really doesn't hit 1 atmosphere until about 835 degrees Celsius, which is the temperature that we need. You can see a little bit before that, you are starting to make some gas, right? A little bit before that in terms of temperature, but until it reaches that sort of standard pressure of 1 atmosphere is not until about 835 degrees Celsius. And again, that would obviously indicate that this reaction happened. Way back here, where like 25 degrees is, there's no pressure, which means you haven't made any gas, right? No product being made. I mean, this reaction is really not taking place at that lower temperature. Any questions on that there? All right, so why don't you give this one a go for this reaction. Delta H is minus 1204. S is minus 216 at 25 degrees. Our reactants or product favored at equilibrium. Under the delta H given to us, we have delta S given to us. So the same equation that we just used would be the most appropriate here. And once again here, we got to convert that into Kelvin. So that's going to still be 298 in this case. So putting it in, we'll take our delta H. And again, I'm going to multiply it by 1,000 to convert it to joules. We will then minus it by our temperature times our delta S, which is in joules. And it looks like we will get minus 1204 times 1,000 minus 298 times minus 216.4 minus 1139513 joules. Again, I'm going to take it back to kilojoules by dividing by 1,000. It says something like negative 1140 kilojoules, perhaps. In this case, is reactants or products favored in this case? This negative delta G would mean that the reaction is probably proceeding which direction? Towards the products, yes. So I would say products would be favored here, kind of spontaneous towards the product side there. And that would allow us to obviously make more products. Any questions on that one there? Yeah. Does it matter? I'm sorry. No, it doesn't. Technically speaking, the moles are still here. Sometimes people will leave it off in this most of the time. The Kelvin kind of gets canceled out there. That's technically there as well. So I'm okay if you leave it in kilojoules. If you want to leave it in kilojoules per mole, which it is still sort of there at that point. The moles go away when we do like products minus reactants one, and we multiply by the coefficient. That takes care of the moles and sort of that one. So sometimes the units maybe don't cancel out perfectly, but this technically would still be kilojoules per mole. Yeah. But if you left in just kilojoules, you'd be okay. For me. Other questions? All right, so let's talk a little bit about Gibbs free energy and phase changes. So when we do have a phase change, as we talked about previously, it does happen at the same temperature, and exactly at those temperatures. For example, at the melting point or freezing point, we have exactly solid and liquid basically happening at the same time. At the normal boiling point, where we transition from liquid to gas, we have basically the same idea, liquid and gas exactly at the boiling point. So if we're talking about, for example, water at 0 degrees Celsius, we again have sort of like ice crystals sort of happening. We got both solid and the liquid phase in equilibrium with each other. A little bit above 0 degrees, you get liquid water. A little bit below, you get basically ice. Same thing at 100 degrees Celsius for water, which is the normal boiling point for water. Again, we get kind of both things happening at that point. Not until you get a little above that you do establish sort of gas, and a little below 100 that you have, again, some liquid sort of happening. So there is, because it's an equilibrium process, the delta G from our equation will equal 0. And if we go and solve for delta S in this case, we could get what is sometimes referred to in this particular case as the delta S of vaporization. And that is the heat of fusion. Heat of vaporization for water. And this is obviously for water here, what we're looking at. And that is the energy that is required to change a substance from liquid to gas. Our gas back to liquid is the heat of vaporization. The heat of fusion is what we use when we go from solid to liquid, our liquid back to solid. That is the delta H of fusion. And as I think we talked about, again, liquid to gas, our gas back to liquid is the delta H of vaporization. It does matter in a sense which way you're going, as one way is an endothermic process and one way it's an exothermic process, but the amount of energy required to do that is the same. So for example, if we were going from liquid to gas and we're talking about water, it would be a positive 40, we'll call it 40.8 kilojoules per mole. If we were going from gas back to liquid, that's an exothermic process, which means energy has to be released. The delta H of vaporization would be a negative 40.8 kilojoules per mole. So the amount of energy is the same regardless of which way you're going, but the sign will be different depending on the direction that you're going. Same thing with our delta H of fusion. For water, for example, as we go from solid to liquid, again, that's an endothermic process, something like positive 6.02 kilojoules per mole. And as we go from liquid back to solid, that's an exothermic process where heat and energy would have to be released. That would be a minus 6.02 kilojoules per mole, which would be exothermic. As you can see from the difference in the temperatures, right, it takes a lot more energy to do the transition from liquid to gas than it does to go from solid to liquid, obviously in the case of water. And that is because as you go from liquid to gas, things are completely breaking apart from each other into the gas phase. They're flying around. So it takes a lot more energy to do that. So these numbers here are obviously specifically for water. If you were dealing with some other substance, two things would be different. Perhaps the delta H of fusion and vaporization would be different for a different substance. And also the normal melting point, freezing point, boiling point would be different. So it won't always be obviously 100 degrees Celsius or 0 degrees Celsius. If you're not dealing with water, they would have their own sort of boiling points, melting points, and those type of temperatures. But what we're looking at here by rearranging this equation, our delta G equation, bringing our T delta S to the other side and our delta H and dividing our temperature over, we get this delta S, and in this case of vaporization, what we're looking at the bottom there, delta H over T. This equation is the one I was talking about earlier that looks just like the equation for the delta S of surroundings, yes, but no negative. Yeah, so these two are always confused, and I would say people always want to put a negative into that equation that we're using here. So for phase changes where you're kind of deriving this equation from the delta G equation, don't add the negative, yes, unless you need the negative, but don't add the negative. Remember, for delta S, the surroundings, it is negative because it is the opposite relationship of the delta H is what we see happen to the surroundings. So that negative is important to be there. It should not be just added to this one in this particular case. So in this particular case, what we're looking at is the phase change of going from obviously liquid to gas in this case. Once again, our delta H of vaporization for water. And this is the normal boiling point of water, right? Normal boiling point is 100 degrees Celsius. You added 273 to it. It is 373 Kelvin. Yeah, so that's 100 degrees Celsius where it happens. Gives us a delta S of vaporization of 109 joules. Our delta H of vaporization in this case is a positive value, which means that the amount of disorder is increasing or decreasing. The amount of disorder is increasing, right? Positive delta S means entropy is increasing, more disorder, which is exactly what we would expect to happen as we go from the liquid phase right to the gas phase. We're going from a more ordered state in the liquid phase to a lot crazier of a state, right? Everybody's flying around in the gas state. Now, let's say we were doing, say, the delta S of condensation, right? And condensation means that we're actually going from gas back to liquid, right? What would all be the only difference in our calculation here? The heat of vaporization should be a negative value as it's an exothermic process over the same temperature, which means we get the same number, except it is now negative, which also makes sense, right? Going in the opposite direction. We're going from things flying around to things that have clumped together into the liquid phase. A lot more order has been established, and we would expect a delta S value in the condensation sort of direction to be a negative value. Any questions on that there? So we can calculate, obviously, like we did here, the delta S of vaporization. We could also do like the delta S of fusion as well, which would be that transition between solid and liquid. The only difference is, obviously, we would use the delta H of fusion rather than vaporization doing that transition. Any questions on that there? Yeah. That is the heat of fusion for water. In kilojoules per mole, it's also roughly 335 joules per gram is the conversion of that in joules per gram. But that's the delta H of fusion for water. And again, if you were not dealing with water, you would probably different value. No chance find other questions. Yep. Okay, so let's try one here. The enthalpy of vaporization for mercury is 58.8 kilojoules per mole. Normal boiling point 630 Kelvin. What is the entropy of vaporization here for mercury? Okay, so taking a look at this again, really this is going to come from our equation that we've been talking about here. Once again, we're talking about the entropy of vaporization, which means vaporization would be going from liquid to gas in this case. That is also going to be, again, a phase change, which means it's in equilibrium with both phases happening at the same temperature. All that is what tells us that our delta G value here would then equal 0 at that equilibrium process, which is typically what will happen. That will then allow us to solve for the delta S, which would be our delta S of vaporization by moving it to the other side. And again, dividing our temperature to this side gives us our delta S of vaporization will equal our delta H over our temperature, which does need to be in Kelvin. So it is in Kelvin. So that's good. This is our delta H of vaporization. As you can see, it obviously is a different value than what we see for water because it's a different substance. And we also see a much different boiling point temperature than we do, say, for water, which is 100 degrees Celsius as well. So again, you want to make sure you use the correct values. Once again, we got this from rearranging our equation here, which means we do not want to add any type of negative like we do with the surroundings, delta S, so we don't get the wrong answer here. So we'll have our 58.5, and I'm going to once again times it by 1,000 because typically S's will be given in joules, so that's why I'm doing that. You don't necessarily have to in this particular case. We will divide it by 630 Kelvin here, and that will get us 58.5 times 1,000 divided by 630, going to give us about 92.9 joules per Kelvin as our delta S of vaporization. It is a positive value, which is what we would again expect here. Going from the liquid to the gas, we're definitely increasing, right, the amount of disorder. So our delta S should reflect that as being a more positive number. And clearly, as we talked about on the previous slide, if we were heading in the opposite direction, really the only thing here that would change is our delta H value would be negative, which would then obviously turn our delta S into a negative as well. And that would also make sense heading in the opposite direction. Yeah. You don't, again, if you didn't, in this particular case, it didn't really give you or tell you what units to use. So technically you can use any unit of energy that's legit, you could use that. But in general, the sort of general units that go with sort of these thermodynamic values are, typically speaking, delta H values are usually given in kilojoules. Delta S values are usually given in joules, and delta G values are usually given in kilojoules. So there's just sort of the common units that you usually will display them. But truthfully, if they did not specify, you really could leave it in any units you want. Other questions? All right, so let us talk about Gibbs free energy and our good friend. I feel like we haven't seen the letter K in a while here, and I know you miss it. So let us talk about it. But before we do, let us talk about a situation that you could think about here, which is this equation, which is another delta G equation. This is delta G is equal to delta G naught plus RT natural log of Q. So you may be saying to yourself, that's a lot of G's in this equation, and it is. So the difference here is one has a naught, one does not. So again, the way you can kind of think of this is the guy with the naught is really standard conditions, right? So that is the guy that you would go to the table, do products minus reactants, right? And calculate the delta G value. You could think of this guy as sort of non-standard conditions, what the delta G would be under sort of non-standard conditions. Remember that when we talk about sort of standard conditions, what that really means is usually if we're talking about pressures, the pressure should be 1 atmosphere. If you're doing anything with concentration, the concentration should be 1 molar. And if you're doing anything with temperature, the temperature should be 25 degrees Celsius. So if it happens to be a case where one of those things are not those values, so maybe you got some pressures that are not 1 atmosphere, maybe you got some concentrations that are not 1 molar, that is sort of like a non-standard sort of condition, and your delta G value will be adjusted based on that. So you'll have kind of like your delta G value under standard conditions, and now you did something to maybe play with the temperature, maybe play with the pressure, maybe play with the concentrations, and it may have an effect on the actual delta G of that reaction because you played with some of these components. And that is what the rest of this equation is for. This is our gas constant, but it is the one that involves energy. So that's the 8.314 joules per Kelvin per mole. The temperature, like most things, does need to be in Kelvin. And the Q is the reaction quotient, which is the same Q that we've used in many places up to this point. It is your concentration, right, of your products divided by your reactants. It's the exact same way that you calculate K, right? You still use, obviously, the coefficients as the exponents. And this would be a situation, again, where probably either your concentrations aren't 1 molar or your pressures aren't 1 molar. That's probably where the change is going to occur. You, again, with this equation, need to be really careful with units. The delta G naught is going to be probably in kilojoules. Your R values in joules. You don't want to, again, be off by a factor of 1,000. So again, somewhere you got to do a conversion either to joules or to kilojoules. Again, it really doesn't matter. Some people like to go to kilojoules in this one because delta G is typically given in kilojoules at the end, which is fine. Or again, you could go to joules and convert to kilojoules at the end. But again, you really do want to watch your units between those two guys, your delta G here and your R value here. And the normal, make sure it's in Kelvin as well. It's a good reminder when you do it. So you can think about using this delta G sort of equation again when a situation arises that something is not under those standard conditions. Probably in most cases, you may be given some concentrations, some pressures, and that's probably the key to recognize that that's probably the one that you should use. Again, in some cases, the delta G naught may be given to you in the problem, or it may not be given to you in the problem. You have to calculate it by going to the table and doing products minus reactants. So, if you find yourself like, I think I'm missing one other number, like that delta G naught, you may have to calculate it yourself in a problem like this to use this equation if it's not provided to you. Now, if we get to equilibrium, which is everybody's favorite thing, our delta G will equal 0. And at that point, it is now going to be the equilibrium constant. It is not going to be Q because we're definitely not equilibrium. So basically, the top equation now becomes 0 is equal to delta G naught plus RT natural log of K. Bringing this to the other side gives us another important equation, which is that delta G naught is equal to minus RT. So that is a negative sign. And natural log of K, which is the equilibrium constant. Also very commonly messed up by people is this top equation. That is a plus sign there, not a minus. Yeah, so keep that in mind that you do not miss that. So when would we use the bottom one? To keep it really simple, we've now seen like 4 equations that have delta G in it, right? We got delta G products minus reactants. We got delta G H minus T delta S. We have our delta G is equal to delta G naught plus RT natural log of Q. And now our delta G naught is equal to minus RT natural log of K. Once again, the best piece of advice is use the one that is appropriate for what you are given in the problem. So anything involving equilibrium constant, find the equilibrium constant. They give you an equilibrium constant, use the bottom one. Anything that has an H and an S, use the one that we've been using previously. Anything that you need to calculate some non-standard conditions, top guy is the one. And frankly, all you're given is the equation. Products minus reactants is the way to go. So that's the best piece of advice, is just kind of use the equation that sort of fits the information that's given to you, is sort of how you could choose properly. Any questions on that there? All right. Obviously, looking at this equation with the equilibrium constant, if you understand equilibrium constant values, which I hope you do at this point, you could still just look at the equilibrium constant value and it really will kind of tell you what's going to happen here. If we have a equilibrium constant value that is greater than 1, that's going to result in a negative delta G, and the reaction is going to be spontaneous, which is what we would expect. The products are going to be favored at equilibrium, because in order to get a large value of K, you need more products, right? So in order to get more products, you need the reaction to go to the product side to make those products. So those two things sort of go hand in hand. If you have a K value that's less than 1, that means, like normal, when we reach equilibrium, we should mainly have reactants, which means that probably will give you a delta G value that's going to be positive, which means the reactants are favored. It's really not going to be spontaneously going to the products. They're going to kind of hang out on the reactant side, which means you will have more reactants than products, which is why you have a smaller value of K. And if you're kind of at 0 or at 1 in terms of the equilibrium constant, both are sort of favored. There won't be very much of one or the other, but it'll be somewhere in the middle there. All right, so why don't you give this a go. Calculate the equilibrium constant for the following reaction at 25 degrees. 203 goes to 302. There's a delta G value. I'm going to give you a delta G value of 02. That is 0 kilojoules. All right. Take a moment and calculate that up. See what you come up with. Okay, let's take a look. So in this case, obviously, we're looking for an equilibrium constant. So that's a pretty good hint here that perhaps our delta G naught minus RT natural log of K would be our good one to do in this case. R is obviously a constant, which is our 8.314 joules per Kelvin per mole. Our temperature converted to Kelvin going to be a 298. And in this case, we are looking for K. So we do need to calculate delta G naught. And again, in most cases, you would probably have to go to the table, obviously, and look up these values. And since really all we have is the equation given to us, we would want to use our delta G naught, right, is equal to our delta G of our products. That's a bad P there. I go minus the delta G of our reactants. And in this case, that would mean for our product side, 3 times 0 kilojoules as O2 has a value of 0, minus our 2 times the value of O3, which looks like 163.4. Gonna give us a delta G naught for this reaction of 2 times 163.4. Looks like perhaps a negative here, 326.8 kilojoules in this particular case. Any questions so far? So now we have our delta G, we've got our R, we got our T, and in this case, we are ready to hopefully solve for this. We're going to put our negative, I think, 326.8 kilojoules. I am, again, just because it's in my head, I'm going to convert it to joules because of the R value. Once again, if you want to convert the R to kilojoules, you can do that, whichever way you want to do it. That is going to equal my negative 8.314, which is my R value, my temperature 298, and my natural log of K. All right, so kind of cleaning everything up and bringing these guys to the other side. Let's see here what we get. We get that times 1,000, I think, divided by 8.314, divided by a 298. And in this case, we will end up with about 131.9 is equal to the natural log of K at this point. To get rid of the natural log, we got to take the E on both sides, I believe. We're going to E that, and we're going to E that up there. When we E the right-hand side there, that pretty much just leaves us K. And again, we're not going to put any negative or anything in there, so we're just going to take the E of it the way it is. And, you know, depending on your rounding, 1.9, we'll go with 1.9 times 10 to the 57, I believe, in this case. Any questions on that there? Based on the delta G value here, reactants or products are favored. Delta G value is negative, which means should be kind of heading towards the product side, right? Which means products are favored. And that means if we're making a lot of products, we should have a large or small value of K. We should end up with a large value of K, right? Which that would definitely qualify. So again, those two things sort of correlate to each other and do make sense based on the values that we got there. Any questions on that there? All right, so why don't you try another one here and see what you end up with. Calculate the delta G naught for the following reaction if the KSP value is 1.7 times 10 to the minus 6. So let's see what you come up with on this. All right, so looking at this one, we once again are looking for a delta G naught. We are given a KSP value. Remember, it doesn't really matter the K value that you're given. They're all basically the same thing. They're all an equilibrium constant. So once again, this makes our choice of equations down to the one that has the K value in it. This would be, again, the right one to choose here. We will take our temperature still, the 298 Kelvin in this case. R is a constant. And in this case, we actually have the K. So this one's pretty straightforward. We're going to just plug it in here, minus our 8.314, which is our gas constant, our temperature 298, and our natural log of 1.7 times 10 to the minus 6. Cleaning up obviously everything on the right-hand side there, we're going to take the natural log of 1.7 to the minus 6 and times it by a 298 and a 8.314. Probably times it by that instead of divide would be a better move. Let's try that again. Times it by 8.314. All right, so I think that looks better. We will end up with a 32,914 joules. Converting that into kilojoules by dividing by 1,000, about 32.9 kilojoules. Our delta G value here is positive, which means reactants or products favored here. This would be reactants, yeah, kind of non-spontaneous, going to hang out on the reactant side, which makes sense with our KSP value, which is small, right? And we know from those KSP values that pretty much those things are insoluble and should stay on the reactant side. So again, you want to make sure that in terms of signs of what you calculate, you know, these things sort of make sense based on the information that's given to you in a problem. Because sometimes, again, people get a little off with the signs sometimes as they're doing some of these things. So just make sure that these things sort of make sense. Any question on that one there? All right, one last one here for chapter 16. Calculate the delta G naught for the delta G naught for the following reaction is 2.6. We got some pressures of each of the gases. We're actually looking for the delta G for this reaction. See what you get there and predict which way it might go. So on this one here, we have a delta G naught, we have a delta G given to us. So really the only one that has both of those type of situations is our delta G is equal to delta G naught. Remember, it is a plus RT natural log of Q. Again, this is sort of non-standard conditions, standard conditions. So the reason it's non-standard conditions here is the pressure part, right? The pressures here are not all 1 atmosphere like it would be under standard conditions. So that is sort of the non-standard part of this problem. But they were nice enough to give us the delta G, which would be what the delta G for this reaction would be under standard conditions if everybody was 1 atmosphere in terms of their pressure. So with that given to us, we kind of have most of what we need here. We will go with our delta G naught. And once again, I'm going to do the multiplying by 1,000 to get that into joules because I do have R here that's in joules. So everything will be okay. Plus R, which is 8.314. Our temperature here is still 25 degrees, so that's a 298 Kelvin. We do want Q in this case, and once again, Q is just like K, so we would get it from our equation. This would be the partial pressure squared of HI from the coefficient, divided by the partial pressure of H2 times the partial pressure here of I2. So we have all those pressures given to us. So this is going to be the natural log of HI's pressure, which is 0.23 divided by, and we do need to square that, right? And we have H2's pressure, which is 4.26, and I2's pressure, which is 0.024 in this case. All right, so I'm going to start with on the right-hand side there. We're going to do 0.23, do a little squaring action. We're going to divide it by 4.26. We're going to divide it by 0.024. That gives us like 0.517. We're going to take the natural log of that, which gives us minus 0.6589. We're going to times it by 298. Again, times it by 8.314. I'm going to stop timesing at that point, I think. We're going to have 2.6 times 1,000 joules plus, I believe we get something like negative 1632.52 and some change. I'm now ready to add those two together. That gets me 2.6 times 1,000 plus my answer, going to get me a delta G value here of looks like 967. Mine would be in joules because obviously I converted everybody to joules. If you did kilojoules, you would be at like 0.967 kilojoules. First off, any question on the calculation here? So our delta G for this reaction is a positive number, which means which way would this reaction kind of go or stay? It's going to stay where? Reactants or products? Positive means really non-spontaneous, not heading to the product. So it's going to be at the reactant side. Yeah. So it's going to hang out over this away towards the reactants, which is sort of where it is under standard conditions, right? Our delta G naught under standard conditions is 2.6, which is also a positive value, which means by playing with the pressures here, we didn't really benefit all that much there. We still ended up with a positive delta G in this case. Any questions on that there? Questions on thermodynamics? All right, that wraps up chapter 16, they say.